Okay. So let's talk a little bit about where we have been and how this is connected to growth. In the last lecture, I talked about the fact that in repeated measures analysis of variance, we make this assumption that the latent variable that is responsible for covariance over the course of time is a tau equivalent or a random intercept model. The random intercept model being where I fix these loadings to 1 and freely estimate a variance, the tau equivalent model being where I fix this factor variance to 1 and freely estimate these loadings but constrain them to equality. And I can set up my design to be either testing a hypothesis about 4 means that are all different, freely estimated, or I can set up my model with an a priori contrast statement where I might pick one measurement occasion and fix that as my mean of the manifest of the random intercept variable, and then come downstairs and freely estimate the intercepts for the remaining ones. And we found out that this is going to give us an estimate of one measurement occasion and the measuring the number of points above or below that reference occasion that the rest of these means are. And these answer different research questions that we're interested in. Coming down to the picture, the repeated measures analysis of variance model is a model of change. And this corresponds in physical form to a very common sense approach to measurement. Repeated measures analysis of variance was born in studies of agriculture, where I'm looking at, say, the weight of animals or the height of corn stalks, things like that. And if I have a ruler and I'm going out to measure, say, how tall my corn plant is, the measurement error in that ruler is the same at time 1 to time 2 to time 3 to time 4, because my ruler has measuring marks on it, and those measure with a certain degree of precision. So it's common sense. Now, as Joy pointed out last time, actually, in behavioral research, this assumption about the measurement error might well be different. Even though the measuring units, inches, centimeters, might be the same in the manifest variables, the degree of precision, measurement precision in those might be different. And if she had been writing the article about 20 years ago, she could have published her idea in Psychological Methods and beaten Kesselman out for talking about the non-parametric repeated measures analysis of variance, which is nothing more than fitting the repeated measures model and allowing these error variances to be different. As structural equation modelers, we might also think, though, that the random intercept model is not optimal for us because of this assumption of tau equivalence. That maybe, rather than having all of these loadings be fixed to be the same, I might want to say, let's fix this factor variance to 1 and allow all of these loadings to be different. This then means that the degree of relationship between variables is different across different measurement occasions. To my knowledge, no one has really looked at that as a way of testing only hypotheses of means that attach to the manifest variables. We start to look at means of this of this factor variable instead, and we'll get into that when we talk about the factor mean model some more. To summarize downstairs, when we're doing other software, we often talk about the R matrix or the standardized R matrix across measurement occasions in repeated measures Anova. And these parts of our printout have meaning to us as structural equation modelers. This is the predicted variance covariance matrix of the data. This is the square of the loading times 1 for the latent variable plus the error term, or it's 1 times the variance of the random intercept variable plus the error term. And over here, this is the covariance between time 1 and time 2. If I standardize this matrix, if I pre and post multiply it by the square root of these variances, I get a correlation matrix out. And this 0.79 indicates in standardized form how associated measurement occasion 1 is with measurement occasion 2. This statistic has a name. It is called the ICC, or the intra-class correlation coefficient. Okay, so that's a summary of where we were. And we now talk about models of growth. And the first one that we introduced last time was the factor mean model. This is saying, as a parsimonious model, I can get away with summarizing both mean level effects and variation and covariation, all by drawing this diagram, because the mean at time 1 is going to be this number times the loading. The variance at time 1 is going to be this loading times the factor variance times this loading, which is 6 to 1. And the covariance between the variables is this loading times the number 1 times that loading. So if true, the factor mean model is a very parsimonious way of summarizing relationships in the data. Think about the adjoint sums of squares and cross products model for these data. It describes 4 means and variances and covariances, or average sums of squares and cross products. 5 times 4 is 20, divided by 2 is 10. There's 14 elements in that matrix, and I'm explaining all of that by saying, oh, hey, there's 1, 2, 3, 4 error variances, 4 loadings, and 1 mean level. 8, 9. Now, in this particular data set, the error variances for time 1 and time 2 were really close to each other, so I made the model even more parsimonious by setting those two to be equal. It looked like at other measurement occasions, there was more error variance at time 4 and less error variance at time 3. The factor mean model, although it was originally proposed in around 1989 by McArdle and Epstein, is not widely used. And the reason that it's not widely used is that it doesn't summarize the data well, because it doesn't make a good assumption about the measurement of the properties. Let me talk a little bit about that with a discussion. Say that these 4 times of measurement represented height. And say we were looking at, say, plants. And I walk out to my field and I see that the plant has not yet sprouted. It is not yet above the soil. What is the factor loading for that particular measurement occasion going to be?
Would it be 0?
Yeah, it's going to be 0. So let's go back and think about the variables that we have in psychology. Usually, having none of something does not correspond to a 0 number. I used to have an instructor at the University of Iowa, H.D. Hoover. I think he's retired now, but he was from the South. He was part of William Tremaine's study of the gifted. But he said, even a blind pig finds an acorn at midnight in the forest now and then. So if you take a test in psychology, say a classroom test, you're going to guess right some proportion of times. Or if you're measuring dogmatism, the least dogmatic person probably has a score that is not exactly equal to 0. So there's some kind of a scale that goes on. Well, this is kind of where I come into the model. And I like to read old things. Actually, this mathematical model was proposed way back in 1967. And I call it the factor mean shift model. Well, what's going on here is, just as you might think in physical measurement, there's an analog here to the factor mean shift model. Now, over the course of years when I was teaching this, my son was very young. He was like 4 years old. And he would pick up my measuring tape. And if you've ever seen them, I should have brought it and done it on video. You pull the measuring tape out and you press the button and it snaps back into the measuring tape. It's kind of fun to do. And I kept saying, Justin, don't do that. It's not a toy. And he'd say, okay, Dad. But of course, he kept doing it. And then after a while, he said, oh, and I then knew something had happened. Well, my measuring tape now no longer starts at 0 inches. It starts at about 13.5 inches. And I thought to myself, I could still do things with that measuring tape. I could, say, judge whether something is whether one piece of wood is longer than another. If I take one measurement and subtract it from the other, I'm still going to get 5 inches. But my measuring tape would now no longer work if I were, say, trying to measure square footage. I couldn't take height by width or length by width and get square feet out of it. If I'm going to do measurements with my broken measuring tape, I'm going to have to subtract a constant or add subtract a constant from everything before I do my measurements. Well, that's exactly what this little common intercept does. It asks the computer program to give me a number that I can adjust my manifest variables by in order to bring these variables into ratio scale. A ratio level scale is something that has a meaningful 0 point. So when I do this model, the fit is really much nicer in many situations. And one of the things I've noticed over the past 5 or 6 years from this class is this model is fairly new. And in those situations where you have a variable that seems to typify growth over the course of time, you can improve the fit a lot by adding a common intercept to those data. This is also a model of mean and variation increasing. So for these data, notice that the mean increases. It doesn't increase in a straight line, but that variation also increases as the mean increases. So, it's kind of the same picture as we saw for the factor mean model. It's just that in the factor mean model, as Joy points out, a score of having no growth corresponds to a value of 0. In the FMShift model, it's the same picture, it's the same thing being described, but having no growth at times 0 corresponds to a score of -20. These 1, 2, 4, and 6 are the measurement occasions in my study. So I've got just a little bit of time so I can show you a picture, and then we'll talk on on Friday about this, that this model of growth is not the one that we usually see. We usually see this picture. And this model has both a random intercept, just as we saw in repeated measures analysis of variance, but also a growth factor. And probably in most of your reading in your area where we've been talking about growth models, there's a constraint on these loadings. That is, I constrain my loadings to follow a straight line. So, I'll just show you some pictures and then we'll come in and we'll talk about that. I can fit this model with either a correlation between the random intercept and factor or orthogonally. And downstairs, later on, I can put some constraints on this. I can constrain these models so that they correspond to the amount of time elapsed since the first measurement occasion. And I can fit a linear growth model that says, oh, all growth in my model has a form and it's a straight line. So that's where we're going in terms of talking about growth. In a nutshell, we're going to be including this random intercept variable, which is saying that the shift, the mean across all measurement occasions, that's the same, is itself an inter-individual difference. So I will repeat that again when we take up the battle again on Friday. All right.